Hello and welcome back to another episode of AWS Cloud Bytes. I'm your host Bhavesh Kumar, and today we are diving deep into our architecture series. Today we are breaking down the two most critical patterns you need to master for API Gateway: the Lambda Proxy for rapid and serverless deployments, and the private VPC link pattern for secure internal backends using ALB and NLB. We are going to look into the silent killers of API performance, throttling and caching. By the end of this video, you will exactly know which front door to build for your AWS services. Let's do a walkthrough to this document. What are you going to learn from this document? You will see how API Gateway fits into modern AWS architectures. You will see public REST HTTP APIs with Lambda Proxy integration pattern. We'll also look into the private integrations with VPC Link and internal ALB or NLB. We'll cover the throttling, rate limiting, and caching behavior in the real world. Let's talk about what API Gateway pattern means. So API Gateway is your front door for your API. It allows you to have routing, which is path-based routing. Security is the next aspect of your API Gateway. Authentication, authorization, resource policies, WAF. They were supported in REST API as well as in HTTP, typically using a CloudFront and WAF combination. The traffic control, such as throttling, quotas, which is basically your usage plan, and request validation can happen for REST APIs. Observability, we'll look into that. We have CloudWatch, metrics, logs, and other hooks that we can have. Let's look into the first pattern. This pattern is about REST or HTTP API with a Lambda Proxy integration. In this case, you are having a public API. So the user logs into a front end and the front end makes a call to this API, or it can be any other client, such as you can use Postman or any curl command to make a call to this API gateway. For the purpose of keeping it simple, I'm not putting anything like Route 53 as your entry point, and we're just focusing on API Gateway as your entry point using the API Gateway DNS directly. So you have the API Gateway, you have REST API or HTTP API. In this pattern, API Gateway has a direct integration with Lambda, and you can see this is a proxy integration, which means request context is fully received by the Lambda. Now, Lambda can talk to any database. It can be a SQL, it can be a NoSQL. In this case, I'm just showing you a DynamoDB, NoSQL DB. And Lambda has native integration with CloudWatch, logs, metrics. All that information can easily go to CloudWatch. Similarly, the API Gateway has a native integration with CloudWatch, logs, and metrics. So this is one of the simplest and one of the most easiest way of building and deploying a serverless application. So when do you go with this particular pattern? This pattern works well for CRUD operations, your webhooks, your lightweight orchestration APIs. Let's look at the sequence diagram to understand the flow. The front end or the user is making a call using the front end. It may be a GET or POST. The API gateway, if there is a quota specified and there are too many requests coming in, and API gateway is throttling you, then you will receive 429 too many requests as a response. In case the API gateway is not throttling you down and you are getting an allowed from API gateway, then you have an option if the cache is enabled at the API gateway, that if the cache is a cache hit, you receive a 200 response or 2xx response from the cache. If it is a cache miss or the cache is disabled at the API gateway level, the request will flow to the Lambda using the proxy event. The Lambda will then subsequently make a call to whatever SQL or NoSQL database it has to fetch data from. A response from that will be then served by the API gateway with relevant status code header and body information. It can be a 2xx, 4xx, 5xx response. So that's the overall flow where you have a Lambda proxy integration. In this case, we are just proxying every header, every method context that you're receiving at the API gateway level, sending all that information to the Lambda, and Lambda can work accordingly. Let's look at the second, which is the pattern 2. This pattern is using the VPC link ALB, NLB, and some private services. When are you going to use this pattern is when you have an internal load balancer, you have private services, you have a private database, but you still want to use a publicly available API gateway. So you can see the typical backend targets. It's ECS or ECS Fargate service behind ALB or NLB. It can be an EC2 instance behind ALB or NLB. It can be an internal service mesh or a legacy application that cannot be a Lambda application. On a note around the VPC link, we are talking about VPC link version 2 that is supporting both REST APIs and HTTP APIs. The private integration can target internal ALB or NLB, which is network load balancer and application load balancer. For HTTP API, it can also integrate with the AWS Cloud Map. The version 1, we are talking about version 2 in this picture, but the legacy REST VPC link version 1 path is only for NLB. Let's talk about the high level flow. In this case, the request comes into the API gateway. The request is then forwarded to the VPC link, which sends it to the load balancer. So the load balancer is then routing it to the relevant private service, and the private service is then talking to whatever database they want to fetch or persist data into and sending the response back. In this case, again, you can have different kind of integrations. CloudWatch is usually available for all these services, or you can have an SDK implementation if it is not a ECS or it is a legacy service that is not natively talking to CloudWatch. Let's look into the sequence diagram. You will see that we have a user front end as a participant over here. Now the HTTP secure request is coming in, HTTPS request. That request is forwarded to the VPC link. VPC link forwards that to the internal load balancer. The internal load balancer then forwards it to the target. Out of those services, the load balancer is choosing one of them, and then the response then flows back, and the final response is reaching the user or the front end. So that's the second implementation or the second pattern how you want to have a private integration. The first one was more of a public. Let's talk about the ALB and NLB decisions. We'll talk about what to pick and why. So let's look into the decision points. We have the first decision point saying API Gateway and VPC link support. You should choose ALB, Application Load Balancer, when you're using a REST or HTTP API, VPC link or version 2. And if you want internal ALB, the NLB is a choice when you need NLB features for REST or HTTP API, or you're running a legacy REST VPC link version 1, which is NLB only. Protocol and features. In ALB, it is HTTP aware behavior, which means you can do the routing, host, path, and you can have HTTP health checks. In case of NLB, if you're looking for TCP, UDP, TLS pass-through, or non-HTTP protocols, then you go for NLB. Routing complexity, you want to route to multiple services using or with rules. So in that case, you will go with ALB because you can do rule-based routing. In NLB, you want simple layer 4 forwarding. Performance profile. This is basically the ALB is used for standard web and API workloads. The NLB, on the other hand, is used for very high throughput, low latency, and high connection counts. In case of static IP requirements, the ALB, it is not required. In case of NLB, you will need a static IP or a elastic IP. Let's talk about the rate limiting versus throttling, the API gateway behavior around that. So throttling is to protect your API from spikes. which means if there are thousands of requests coming in, you want a steady state and the bursts can be handled. Anything that goes beyond the burst that is allowed, you throttle those kind of requests, and then you receive 429 when the burst is too high to be served. So that is where the throttling kicks in. Usage plan, quota. When you create a REST API, you create a user API usage plan. And this is good in places where you want to restrict, or when you are selling this API to a client for, say, 10,000 requests in a month. And that is their usage plan. So you will allow 10,000 requests to go through and then you will stop it. So given that quota for that day, week, month, you can handle how many requests a client can do, and you can charge based on the request. Concurrency, back pressure. Our API gateway usually, in case of AWS, API gateway is usually managed. So the scaling is not an issue, but then you will have to be cognizant about your downstream services, such as Lambda has 1,000 concurrency by default. And similarly, if your other services are not able to scale accordingly, even if you don't put any kind of throttling or a usage plan on your APIs, and you allow a large number of requests to go through your API gateway, and your backend or downstream services are unable to handle it, in those cases, again, your application will fail. So that's what concurrency back pressure is trying to summarize, that your downstream may throttle even if your API gateway can accept it. What are the practical guidance around this? When you set up an API gateway, you put throttling based on what your backend can safely handle. And you should use exponential backoff with jitter on clients for 429 and any kind of transient 5xx errors. Let's talk about the caching behavior. What to cache and where to cache. So API gateway caching, which is common with REST APIs, you can define the time to live or TTL. So any kind of GET request or GET styled endpoints you can cache. You can define TTL, you can define a cache key, which can be a path or a combination of path, query params, or headers you choose. Rules of thumb, cache only truly cacheable responses that are like public data or safely identifiable user-specific data. If the responses are different for different users, or it is very specific to user that you want to cache, then your cache key must have something that is a user-specific identifier. And you can explicitly have your TTL to be lower, or you must have a policy around how you want to invalidate the cache in case you want to do it. It can be an automated invalidation or a manual invalidation. For HTTP APIs and general edge caching, like if you want to have a CDN-like caching, you should use CloudFront. Choosing REST API versus HTTP API. Use REST API when you need something like advanced API gateway features, built-in caching, request response, throttling experiences, usage plan, API keys, those kind of features you need. Use HTTP APIs when you want a modern, low latency, cost-effective front door, usually for the web and the mobile APIs. Let's take a look at the production checklist. A request and response limit, be mindful of payload size. API Gateway has a hard integration timeout. Usually by default it is 29 seconds. A couple of years back, AWS has now allowed you to have a custom timeout. I think it goes up to 3 minutes. Authorization at the edge. API Gateway allows you to have things like Lambda authorizer that can authorize the request, allow or deny a request. Idempotency for put and post that create side effects. Use idempotency keys to prevent duplicates on retries. Observability, enable access logs, add correlation IDs, which is basically your identifier across multiple hops. So you can have one single correlation ID that can hop into multiple requests. And then you can see how your request has gone from point A to point Z. You should also add alarms on 4xx, 5xx, 429, those kind of errors. Caching safety. Never accidentally cache user-specific data as public data. So those are like some production checklists you should keep in mind. This is the end of the episode. Please like, share, subscribe, and press the notification bell icon for future updates. I'm your host Bhavesh Kumar signing off. Thank you.